Hi, Dr. Jennifer Fogarty from the NASA Johnson Space Center, currently in the Space and Clinical Operations Division, working as a clinical translational scientist. So today we're here to talk about a variety of things with application from ISS into exploration. One of the issues to discuss is how we collect data and then extrapolate and interpret for application to something like an exploration mission. What we try to do is take data points before the flight, during the flight, after the flight, and try to make sense of what change we can measure and what that might mean for missions of various durations. The constraints around trying to take data points during flight can be pretty extreme because of the limitations for mass, power, volume even on a large platform like ISS. Can't have something like an MRI to help us see inside the body and the changes that are occurring, so we have to be pretty creative with what we measure and how we measure it, and it's not always possible. So a variety of our data are done only before and after the mission, and that tells us a change, a delta over time. And a lot of times you can only, based on those two data points, draw the curve between those lines any way you'd like. And then we're asked to say, well, if you're going to go on a 12-month mission, how do those results apply from what you know from 6 months? And that can be very challenging. If a change were to plateau, say, in the first 3 months, then a 12-month mission wouldn't be different than a 6-month mission. But if the change is gradually occurring over the entire course of 6 months and we don't know when it's going to plateau, 12 months could be very different from, much worse than, a 6-month mission. So we try to understand how do we apply this with some level of conservatism so that we don't over or underestimate the medical risk or the performance risk that might be occurring due to the change. One of the best examples is the bone loss. Right now, you'll see in the literature bone loss is calculated about 1.2% per month, but that's really based on a test that's done only before and after flight, and then it's divided by the number of months you've been away. The way the body may work is that bone loss might actually only take 3 or 4 months to actually plateau, and you would stop losing based on the lack of gravity. And that would mean that over the course of 12 months, it wouldn't be any worse than a 6-month mission, but we don't know that. So we have to get creative and use different modalities or use, say, a blood sample and some correlated measure, not the imaging measure that you traditionally use. Bone loss occurs when the body is no longer loaded and bone doesn't have to maintain the same density. So you actually lose calcium out of the bone. And it's an appropriate change, adaptation to the lack of gravity. Unfortunately, it also makes your bone more likely to fracture when it's put under a load or exposed to a certain stress. So for our purposes, or even purposes here on Earth, people are concerned about bone fracture. We see a lot about osteoporosis and preventing osteoporosis. It's a contributor to morbidity and mortality in the elderly. We also know that it can compromise your other systems because when you're losing calcium, your kidneys have to process it. So during something like a space mission, the lack of bone loss, while it isn't an extreme risk because there's no gravity or load, the calcium that your body has to process creates now a kidney stone risk. So it has a dual impact for us. When the crew members come back and are re-exposed to gravity and stresses and loads, the lack of bone density, the bone loss, actually becomes of critical concern to us because of the fracture risk and getting them back to being able to do the activities of normal life and things that they enjoy and be the active individuals they are. And once you reload, your body can start to readapt and start to add calcium back and bone density in a little different way. It doesn't exactly replace itself the way it was lost. So it's another adaptive response we're trying to understand. So when we're trying to understand the risk for exploration missions, given kind of the constraints around extrapolating from a 6-month mission and given the upcoming 12-month mission on ISS and the fact that we're being given more time on ISS to study these things with the extension of the life of ISS out to 2024, we want to plan a research portfolio that helps answer some of these questions. But right now, we really wouldn't be able to answer with a lot of confidence how much bone loss would occur over an exploration mission, say, to Mars. We have some idea on the 6-month transit to the planet what would occur to their bones given the countermeasures we have in place if we were able to have such robust equipment on a small volume. But when they land on Mars, they're going to be exposed to 3/8 of Earth's gravity, which could be a significant enough of a load to really stress their bones. They're expected to get out in an EVA suit, traverse the planet, do activities, even potentially build a habitat. And those type of activities concern us from an injury risk to their bones, to their skeletal muscle structure. After they spend some time on 3-HG, which may reduce the amount of bone loss they experience, it may be similar enough to gravity here on Earth that their body treats it as 1G. We also have some questions about that. But then they have to traverse back in microgravity. So they will be returning to Earth with 12 to 18 months of microgravity exposure. And at this point, we would be guessing at the amount of bone loss over that time and trying to account for the countermeasure that we would put in place to mitigate the loss.